Hello everyone, welcome to this video. In the last video we saw that finite fields must have order which is a prime power of prime. That means it is of the form p to the power n, right? So now if you are given a field with 5 raised to power 12 elements in it, so what is the total number of subfields that it may contain? To answer this, let us use the subfield criteria. So what is that? For that, assume let FQ be the finite field. This be the given finite field, right? With the number of elements Q is equal to P to the power n elements. Then every subfield of FQ has order P to the power m. Where what is this m? Where m is a positive divisor of n. Conversely, this is one part. If m is a divisor of n, that is, we can say that m divides n, then there exists exactly one subfield of this given field FQ with p to the power m elements. So you see this result is very useful. What does it say? It says that if you have the field with p to the power n elements, then the subfield would be that which has p to the power m elements, where this m divides n. Moreover, if they are saying if m divides n, then there exists exactly one subfield of this field having p to the power m elements. So let us see the utility of this result. Let us see some examples. So let us see the one with which we have started. So we had a field with 5 to the power 12 elements in it, right? So the number of elements in its subfield, what is it? So you are to look for those values of m, those divisor m which divides 12. So how many of them are there? It is 1. 1 divides 12, right? Then 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12 and 12 divides 12. So in total we have 1, 2, 3, 4, 5 and 6 subfields, out of which we have 5 proper subfields. Why this is not proper? Because it is itself equal to the field. Therefore, its subfields contain 5. Here the prime number is 5. So 5 to the power 1, 5 to the power 2, 5 to the power 3, 5 to the power 4 and 5 to the power 6 elements respectively. So we have 5 subfields, each containing these number of elements within themselves. So this is one such example. See how simple this result makes the things, right? So let us look at another example. So example number 2. Let us take a field F having 2 to the power 6 elements. So our guess would be that the subfield may contain 2 to the power 1, 2 to the power 2, or 2 to the power 3, or 2 to the power 4, or 2 to the power 5, or 2 to the power 6 elements within it, right? But you see, 1 divides 6, so this is possible. This is also possible because 2 divides 6. 3 divides 6, this is also possible. 4 divides 6, no. 5 divides 6, no. 6 divides 6, yes. So you clearly see that these number of elements cannot be present in the subfield, whereas the subfields exist having 2 or 4 or 8 elements within them, right? So this is one example. Let us see another example. If you have a field with 3 to the power 8 elements, then how many proper subfields it contains? How many proper subfields does this field, let me say this is F, having order this much, right? So this field F has, right? So can you tell me how many fields are there, subfields are there? So you just have to look for this 8 and look for the divisors of this 8. So we clearly have 1, 2, 4 and 8, but 8 we will not take up 8. Why? Because it would result in the improper subfield, which is because it would lead to the field itself. So that is why we'll only take the subfields having elements 3 to the power 1 or 3 to the power 2 or 3 to the power 4. So that is it for this video. Thank you for watching.